Welcome to the AudioML Papers podcast. This week, we're really digging into some brand new research, stuff that feels like it's setting the stage for what's next in AudioML. We're talking foundational work here, not just small tweaks, things that could really shape future generative models, recognition systems, the whole lot.
Absolutely. It's been a pretty big week. We've got 3 papers lined up that, honestly, anyone following the field needs to know about. First up, there's Tsinghua University. They've done something pretty revolutionary in the latent space for audio super resolution. We'll unpack that.
Okay.
Then second, there's this huge effort on unified speech-to-speech translation, trying to get everything, expression, content, translation into one model. Monumental task.
Wow, okay.
And third, something really practical from Google DeepMind, a scalable way to personalize ASR specifically for dissecting speech, which is, incredibly challenging.
Right.
So, our goal today for you listening is pretty straightforward. We want to give you the real nuts and bolts breakdown, the architectures, the training details, why these things actually work, and what the longer-term impact might be. Get you up to speed fast.
Perfect. Let's jump right in then, starting with that Tsinghua paper. AudioLBM, right? Audio super resolution with latent bridge models.
Yeah.
So the goal here is taking, say, pretty standard 16 kilohertz audio.
Yeah, maybe even lower sometimes.
And blowing it up to, 192 kilohertz. That sounds almost sci-fi. Super high fidelity.
It is an incredible jump in quality, but what's really under the hood is fascinating from an engineering standpoint. The core isn't just like a fancy filter bank. It's built on a convolutional VAE, a variational autoencoder.
Okay, VAE, so compression is the name of the game there.
Exactly. VAE's job is to take that input waveform, the raw audio, and squash it down into this continuous latent space, a much lower dimensional space where the information is hopefully really dense and well organized.
And that smooth latent space is crucial for the next step, right? For actually generating the high-frequency details.
Precisely. It makes it easier for the generative model that follows to kind of fill in the gaps, to interpolate cleanly.
And they got pretty specific about that latent space. The representation, popularized, it's only at 100 hertz. That seems really low temporally.
It is low, 100 hertz frame rate, but they compensate by using 64 channels. So they're trading time resolution for feature richness in the channels.
It's a classic trade-off. Did they justify that specific compression level?
Oh yeah, they ran ablation studies, and they found this pretty massive downsampling factor of 512 was the sweet spot.
512x downsampling.
Yeah. That's where they found the best balance between making the latent space manageable, efficient, and keeping enough detail so the reconstruction quality didn't tank.
Yeah, VAEs, notoriously tricky beasts to train, especially for high-fidelity stuff. You always worry about posterior collapse, where the decoder just ignores the input. How do they stabilize this? Must have needed some specific hyperparameters.
They did. 2 really crucial things stick out from the paper. First, they sent the KL divergence weight to 0.
0. Really, isn't that kind of breaking the VAE rules?
Right.
The KL term is what makes it probabilistic, forces that Gaussian prior.
It is a bit radical, yeah. But pragmatic. By setting it to 0, they're basically saying, look, we care more about perfect reconstruction than strictly enforcing a Gaussian latent space. They're prioritizing fidelity.
So it becomes more like a powerful, nonlinear autoencoder specifically tuned for compression.
Exactly. Optimized purely for getting a really good, compact representation for the next stage. They didn't need the probabilistic guarantees as much as they needed that clean compression.
Makes sense for their end goal. What was the second thing?
A latent scaling factor, Esslers. They set it to 0.25. It's a small detail applied to the latent vector before the decoder. Just another knob to help keep things stable during training, stop the latent variables from blowing up or vanishing.
Right, those little engineering tricks that make all the difference. Okay, so they've got this stable VAE making a good latent representation. Now, the core innovation, the latent bridge model, LBM. Why is this different or maybe better than just sticking a standard diffusion model on top of the latent space?
Yeah, this is where it gets interesting. Standard diffusion models, they typically start from pure noise, Gaussian noise usually, and they learn to denoise that step-by-step back into something meaningful, like an image or audio.
Right, the standard process.
The LBM flips that script a bit. It defines a stochastic process, a bridge that connects 2 known informative distributions. It connects the latent code of the low-res audio, ZLR, to the latent code of the high-res audio, ZHR.
Ah, so it's not starting from nothing. It's learning a path between the low-res and high-res representations in that latent space.
Exactly. It's literally bridging those 2 points. This makes the generation task much more constrained, more guided. You're not wandering randomly from noise. You have a clear start and end point in this compressed space.
That sounds much more efficient. Like guided denoising, but all happening at that 100 hertz latent level. What architecture did they use inside the LBM for the actual prediction?
They tried a couple of things, but they found that a noise predictor worked better in this latent space than a data predictor. So predicting the noise to subtract rather than predicting the clean data directly.
Okay.
And the backbone for that noise predictor, a DIT, a diffusion transformer.
Transformer. Makes sense given it's working in that compressed latent space.
Mm-hmm.
Need that attention mechanism for long-range dependencies.
Precisely. In that 100 hertz latent space, information is dense but spread out temporally. A transformer with its attention heads is much better suited than, say, a pure CNN to capture those long-range correlations needed for coherent audio over longer stretches.
Okay, architecture makes sense,
Okay.
but the scale, the training data sounds immense.
It really was, around 5,000 hours of audio, and it was mixed speech, music, general sounds. Crucially, they were really strict about quality. Anything below 32 kilohertz got thrown out. You need pristine data if you're aiming for 192 kilohertz output.
Absolutely. Garbage in, garbage out, especially at that resolution. Did they do anything clever with data augmentation?
Yeah, this I thought was quite smart. To make the model robust to different kinds of low-res input it might see in the wild, they used dynamic low-pass filtering during training.
So simulating different kinds of bad input.
Exactly. But not just one fixed filter. They sampled the cutoff frequencies randomly from a uniform distribution between 1,000 and 20,000 hertz. And they even randomized the filter type, Chebyshev, Butterworth, you name it.
Ah, that's clever. So the model learns to undo any kind of low-pass degradation it encounters, like adversarial training on the input quality.
Pretty much. Builds robustness.
Okay, let's talk model size. The main model, the one going from any input up to 48 kilohertz. How big was that?
That primary model clocked in at 0.5 billion parameters, 500 million. Pretty hefty.
500 million, and then they didn't stop there, right? They got to 96K and 192K using cascaded models.
That's right, a cascaded approach. They trained separate models for the next stages, one for 48K up to 96K, and another for 96K up to 192K.
And how big were those? Still big.
Still substantial. Each of those cascaded models was 0.3 billion parameters. So you've got 0.5b plus 0.3b plus 0.3b. We're talking over 1 billion parameters in total across the cascade.
That's a serious amount of compute. But hang on, cascading models, isn't that inherently risky? If the first model makes a tiny mistake, introduces a little artifact at the 48 kilohertz stage,
Yep.
doesn't that just get baked in and potentially amplified all the way up to 192 kilohertz?
Yeah.
How did they deal with error propagation?
That's the million-dollar question with cascades. And yeah, it's the main potential weakness here. They acknowledge it. They try to mitigate it with something they call prior augmentation.
Prior augmentation, what's that?
Basically, when training, say, the 96 kilohertz model, they don't only feed it the ground truth 96 kilohertz audio, they also feed it synthetic 96 kilohertz audio that was generated by the 48 kilohertz model they just trained.
Ah, so you're explicitly showing the second model the kinds of mistakes the first model makes.
Exactly. You're teaching the downstream model to recognize and hopefully correct or work around the typical artifacts introduced by the upstream stage. It makes the chain a bit more robust than just training each stage in isolation.
That is clever. Training on the failure modes.
Okay.
And the training regime itself sounds like it must have been intense.
Oh, yeah. For the main 0.5b parameter model, they used an effective batch size of 128, trained for 1 million iterations. That's a lot of gradient steps.
1 million steps.
And getting to that final ultra-high 192 kilohertz resolution, that required another 500,000 steps of fine-tuning just for the last cascaded model.
Wow. 500,000 extra steps just for that last jump.
Yeah.
Really shows the diminishing returns and the difficulty of nailing that extreme high-fidelity regime.
Definitely. So putting it all together, AudioLBM is pushing state-of-the-art fidelity, no question. But the cost is significant. It's computationally heavy. That cascade introduces complexity and potential error propagation, even with prior augmentation. Inference speed could be an issue, too.
And the data barrier seems huge.
Massive. Training that 192 kilohertz model needs tons of super high-quality audio sampled above 64 kilohertz. That kind of data just isn't easy to come by for most research groups. It limits who can really play in this ultra-high-fidelity sandbox.
Right, a real bottleneck for wider research. Okay, so from generating pristine audio, let's shift gears. Let's talk about understanding and generating speech across languages, but keeping the feel of the speaker. That second paper. Unified expressive speech-to-speech translation.
UniSS is tackling a really ambitious goal. One single model to handle everything. Listen to source speech, understand it, translate it, and then generate the target speech, all while trying to keep the original speaker's prosody, emotion, their vocal identity.
That sounds incredibly complex. One model for all that.
One massive model. And they built it smart, leveraging a strong foundation. The core architecture is a single autoregressive transformer, but critically, it's built upon Qwen 2.5 1.5b instruct Qwen.
Right, that's one of those big open source LLMs. So they're basically injecting all that pre-trained language knowledge into their speech model from the start.
Exactly. It's a huge head start, especially for the translation part. But because the model has to handle text tokens, acoustic tokens for meaning, acoustic tokens for speaker identity, they had to massively expand the vocabulary.
How big are we talking?
The final vocabulary size is 180,407 tokens. That's enormous. It just shows the overhead needed to juggle all these different types of information, different modalities within one model's context window.
Okay, so how does it actually handle these different modalities? The paper talks about a triple tokenizer strategy. That sounds like the engine room.
It really is. It's how they feed the different facets of speech into this single transformer. You need distinct token streams for distinct jobs. First, there's the speaker tokenizer. They use bicodec for this, which is a very strong audio codec. Its job is to capture the non-linguistic stuff, the voice timbre, the rhythm, the emotion, and it compresses all that down into just 32 tokens, a fixed-length representation of who is speaking and how.
Okay, 32 tokens for the voice identity and style. Then what?
Second, the linguistic tokenizer. This one's from GLM4, another LM lineage. This focuses purely on the content, what's being said. It encodes the speech linguistically at a rate of 12.5 tokens per second.
And this separation was important, wasn't it? They tried something else first.
Hugely important. This is a key finding. They initially tried using bicodec semantic tokens for the content as well, hoping one tokenizer could capture both meaning and style.
Yeah.
Disaster. Performance plummeted. They reported a 15 BLEU point drop in translation quality.
Wow, 15 points. That's massive.
It's definitive proof, really. For complex tasks like translation, those semantic tokens that blend meaning and style just aren't precise enough for the linguistic heavy lifting. You absolutely need a separate, dedicated linguistic token stream for accurate content understanding and transfer.
That's a really valuable insight for anyone building multimodal speech systems. Don't skimp on the linguistic representation for translation. Okay, so speaker tokens, linguistic tokens. What's the third one?
The third is the semantic tokenizer, also from bicodec, interestingly. But this one is used primarily at the output stage for generating the target speech waveform. It operates at a much higher rate, 50 tokens per second.
So lower rate linguistic for input understanding, higher rate semantic for output synthesis.
Exactly. The higher rate gives the model the fine-grained control needed to actually synthesize expressive-sounding audio in the target language.
Okay, tokenizers make sense. Now, how do they actually leverage that big Qwen LLM foundation for the translation task itself? They mentioned cross-modal chain of thought or CoT. How does CoT work in speech?
Yeah, CoT in LLMs is usually about making the model show its work for reasoning tasks. Here, they adapt it to bridge the modalities for translation. It's about explicitly using the LLM's text-based translation skills. They have two modes. The main one, the quality mode, is used for training and getting the best possible results. It forces the model to articulate the intermediate translation step.
How does that look in terms of input and output?
The input is the source speech, represented by its speaker tokens and linguistic tokens, SRC, SPK. The output the model generates is then a sequence. First, the transcribed source text, PSRC, then the translated target text, KTGT, and finally the semantic tokens for the target speech, STDASM.
I see. So it goes, listen, tan, state, amaro, translate, nay, speak. By forcing those text steps, TDGT, they're basically supervising the model using the LLM's strong text-to-text translation ability.
Precisely. It's a powerful way to transfer that knowledge into the speech domain.
And then there's a faster mode for deployment.
Right, the performance mode. Here, the output sequence is shorter, input is the same, but output is just TTGT, CTGTC. It goes straight from listening to generating the translated text and then the target speech token.
So it skips explicitly outputting the source transcription.
Correct. It assumes the model has learned the translation logic internally during the quality mode training, so it can perform faster inference by omitting that intermediate step.
Clever. But again, And architecture this complex, the training must be absolutely critical. Tell me about this 3-phase progressive training recipe. Sounds intense.
It is, and it really highlights that modern SOTA models aren't just trained end-to-end in one go anymore. You need these carefully staged phases. Phase 1 they called alignment. This was about basic multitask learning, teaching the model the fundamentals of ASR, TTS, speech-to-text translation, S2TT, and standard machine translation, MT.
What kind of data?
A massive amount, 77,100 hours of speech data, plus 2.3 billion machine translation text tokens. They hit it hard and fast. High learning rate, 84, huge batch size, 2.3 million tokens for just 3 epochs. Goal was rough alignment across modalities.
Okay, phase 1. Get the basics down, then
Phase 2, Kotai introduction. This is where they started teaching the chain of thought structure. They mixed the phase 1 data with a specific data set called UniSS general, about 45K hours, using a 2.1 ratio. Total data exposure here was 55 billion tokens.
And the learning rate?
Dropped significantly down to 2E4. This phase is slower, more careful. It's about getting the model to properly learn that internal listen, transcribe, translate, speak logic from the quality mode prompts.
Makes sense. Stabilize after the initial blast. And phase 3.
Phase 3, refinement, pure focus on quality. They fine-tuned only on a high-quality subset, the UniSS high-quality dataset, around 20K hours, about 10 billion tokens total. And here they used a very specific learning rate strategy. Started low at 5E5 and decayed down to 5E6 using a cosine schedule.
Ah, that classic final squeeze, a rapid drop to really nail the fine details for expressive speech generation.
Exactly. It helps the model settle into a really sharp minimum in the loss landscape needed for nuance.
Incredible engineering.
Yeah.
So with all this work, what are the caveats, the limitations of UniSS right now?
Well, the most obvious one is language coverage. Currently, it's Chinese English only. Scaling this to many language pairs would require enormous amounts of parallel expressive speech data, which is, hard to get.
The data bottleneck again.
Yeah.
Anything else?
The bigger concern, I think, is the fragility we touched on earlier. That quality mode, the one that gives the best results, relies entirely on getting that first step right, the transcription of the source speech TSRC.
The internal ASR has to be perfect, basically.
Pretty much. If the input speech is tricky, strong accent, background noise, or maybe dysarthric speech and the initial transcription is wrong, the whole chain breaks down. The translation will be based on garbage text.
So it doesn't solve the robustness problem for difficult inputs. It just relies on another system, the ASR part, to solve it first.
Exactly. It's a potential single point of failure for challenging real-world audio.
That's a really important constraint, and it leads us perfectly into the third paper, which directly tackles that kind of challenging input. The Google DeepMind work on dysarthric speech recognition using meta-ICL.
Right. This paper shifts focus completely. It's not about massive generation. It's about highly personalized, accurate recognition for speakers whose speech patterns are significantly different due to conditions like dysarthria.
And importantly, they emphasize the method here, not necessarily a brand new architecture from scratch.
Correct. They use Gemini 2.5 Flash as the base model. But the key point is they only fine-tuned the LLM layers. The audio tokenizer part of Gemini was kept frozen.
Interesting. So they're saying the base Gemini audio encoder is already good enough at capturing the necessary acoustic features, even for dysarthric speech. The magic is in how you teach the LLM layers to interpret those features for a specific person.
That's the implication. It suggests the bottleneck isn't feature extraction, it's the adaptation or personalization mechanism. And their novel strategy is this hybrid meta-training.
Hybrid meta-training. Okay, break that down. What makes it hybrid?
It's a dual-objective approach during training. They feed the model 2 kinds of examples mixed together. First, standard zero-shot examples. Just a piece of audio and its correct transcript, audio text. This teaches the model general ASR capabilities for the types of speech patterns found in dysarthric speech, luring across many speakers.
Okay, general robustness. What's the second type?
The second type is the core innovation. 10-shot examples. These are formatted specifically for in-context learning, or ICL. Each 10-shot example looks like this. You give the model a support set containing 10 audio-text pairs, all from one single speaker. Then you follow that with a query audio from that same speaker, and the model has to predict the transcript for that query.
I see. So within the training data itself, you're forcing the model to practice. Here are 10 examples of how person X talks. Now, transcribe this 11th example from person X.
Exactly. It's explicitly training the model to perform in-context personalization. It learns how to learn a specific speaker's vocal characteristics just from the examples provided in the prompt context window. Meta-learning for personalization.
That sounds potentially way more data efficient than trying to fine-tune a huge model for every single speaker, which would need tons of data per person. Did they show efficiency gains?
They did, and this is maybe the most striking result for practical applications. They ran an ablation study and found something remarkable. A model trained on just 2% of their total training data specifically, a mix of 40,000 of those 10-shot examples, and 10,000 shot examples achieved 70% of the total performance improvement they got from training on the full data set.
Wow. 2% of the data gets you 70% of the way there. That's incredible efficiency.
It really is. It suggests this hybrid meta-training approach is incredibly effective at distilling that personalization capability very quickly without needing massive data sets or endless training time.
And the data sets they used for this were Euphonia and the Speech Accessibility Project, SAP.
Yep, standard, well-regarded data sets for research in this area. But the efficiency story gets even better when they looked at which examples you use for the in-context learning part. The curation matters.
Right. For the 10-shot or fewer shot prompts at inference time, does it matter which 10 examples you pick for a given speaker?
Immensely. This was another key insight. They tested an oracle method for selecting the support examples. This oracle knew the transcript of the query audio beforehand, which you wouldn't know in reality, of course.
Okay, a theoretical best case.
Right. And this oracle selected support examples whose text was most similar to the query text. What they found was stunning. Using this oracle selection method, they could achieve the same level of personalization accuracy with just 5 carefully chosen examples as they could with 19 randomly chosen examples.
5 versus 19. That's a massive difference for the user. Imagine someone with dysarthria having to record only 5 phrases instead of 19 to get the system personalized.
Exactly. It dramatically lowers the barrier, the enrollment effort required from the user. It shows the model doesn't just need more data in the prompt, it needs relevant data. The right 5 examples are much better than 19 random ones.
Huge usability implications. But the catch, that oracle method isn't actually deployable, is it?
That's the critical hurdle for real-world use. The oracle relies on knowing the answer, the query transcript, to pick the best examples, which is impossible in a live ASR system.
So in practice, you'd need some other way to select those 5 best examples automatically.
Precisely. You'd need a proxy method. Maybe you'd select based on acoustic similarity between the incoming query audio and a library of the user's pre-recorded enrollment samples. Or perhaps use a quick, less accurate first-pass ASR to get a rough transcript guess, then use that for text similarity.
But calculating acoustic similarity reliably, especially for very diverse dysarthric speech, is still a really hard problem, right?
It's a major open research challenge. So while Meta-ICL shows the potential for highly efficient personalization with just a few relevant examples, actually finding those relevant examples automatically and quickly in a real-world deployment, that's the next big problem to solve.
And performance, while impressive, is still in a constrained research setting. Real-world noise, different mics, always challenges.
Always.
Okay, fascinating. Let's try and synthesize across these 3 papers now. We've seen super resolution, unified translation, and personalized ASR. Stepping back, what are the big common threads or trends you see emerging?
I think the most striking commonality, really across all 3, is that the latent space is king. Nobody is really trying to solve these super complex problems purely on the raw audio waveform anymore. Everything happens in some kind of compressed, abstract representation.
Yeah, we saw that very clearly with AudioLBM. Their whole bridge model operates in that 100 Hz VAE latent space. It's completely abstracted from the waveform.
Right. And UniSS, it relies entirely on those discrete tokens, linguistic tokens for content, speaker tokens for identity, semantic tokens for generation. It's all happening in the symbolic tokenized domain.
Even the Meta-ICL paper, by freezing the audio tokenizer from Gemini.
Exactly. They're implicitly saying the important acoustic features are already captured well by this frozen encoder. The real task is learning the mapping from those abstract features to text and how to adapt that mapping on the fly. It's all about manipulating information in these compressed or tokenized latent spaces.
So the field is converging on the idea that solving things in abstraction is more tractable, more efficient. Let the early layers handle the messy waveform to representation conversion and focus the big model parameters on the core task logic in that cleaner space.
That seems to be the dominant paradigm right now. The second major trend I see is the sophistication of the training process itself. Simple end-to-end training just doesn't seem to cut it anymore for these SOTA results. We're seeing these intricate hybrid and progressive training recipes.
Right. It's not just about the architecture. The how you train it is just as complex and critical. The recipe matters as much as the ingredients.
Absolutely. Look at AudioLBM. They didn't just train one model. They had the cascaded models with specific prior augmentation and fine-tuning stages for the higher resolutions. It was sequenced.
And UNIS has that incredibly deliberate three-phase progressive strategy. Alignment, then COT introduction, then refinement. Each phase with different data mixes, different learning rates, different objectives.
Yeah, meticulously planned. And the dysarthric ASR work with MetICL, that core idea was the hybrid 0-shot plus 10-shot training objective, mixing general learning with explicit in-context learning training. It all points to this. Building top-tier models now requires really careful engineering of the training pipeline itself, sequencing the learning, mixing objectives, strategically decaying learning rates. It's become a multi-stage design problem in its own right.
So we have these powerful models trained with complex recipes operating in latent spaces. What's missing? Based on these papers, where are the current blind spots or gaps in the research focus?
Two things jump out at me. First, despite all the focus on performance metrics like wear or fidelity scores, there's relatively little discussion about the practicalities of inference speed and computational cost.
Yeah, we're talking models with 500 million, even up to 1.5 billion parameters here.
Exactly. How are we supposed to run these monsters in real time, especially on edge devices or in resource-constrained settings? There's a gap in research focusing on efficient deployment distillation, quantization, maybe architectural changes specifically for low latency. The results are amazing, but can we actually use them efficiently?
It feels like the capability is outpacing the practicality of deployment sometimes.
It often does in research, but it's a crucial gap to bridge. The second area is, maybe predictably, ethics. Papers like AudioLBM and UniSS enable incredibly powerful generation and voice cloning, high-fidelity, expressive, personalized voice synthesis. The potential for misuse is obvious.
Deepfakes, scams, misinformation.
Right. And while the papers might briefly mention ethics, there's no standardized framework being proposed or adopted for evaluating these risks or building in safeguards. We need a more concerted effort from the community to develop ethical guidelines and potentially technical watermarking or detection methods before these technologies become widespread. We need to be proactive.
Agreed. Important points. Okay, let's wrap this up. Time to summarize the key takeaways for everyone listening. First, it seems clear that mastering the training process itself, these complex recipes, progressive learning, hybrid objectives, even clever hyperparameter choices like setting KL to 0 when needed, that's now absolutely critical for pushing the state of the art.
Second, everything is moving towards latent representations. Whether it's continuous spaces from VAEs or discrete tokens, solving complex audio tasks happens in these abstracted domains now. Raw waveform processing is taking a back seat for the core logic.
And third, personalization is clearly a major frontier. The MetaACL paper showed it can be achieved with surprising data efficiency using in-context learning, potentially breaking the old bottleneck of needing huge speaker-specific datasets.
Yeah, these papers together really point towards a future of perhaps more unified models handling multiple tasks, but with a much deeper focus on the entire pipeline, from smart data curation and augmentation all the way through complex training recipes to, hopefully, more efficient and ethical deployment.
It's a rapidly evolving landscape. Fantastic breakdown. Really appreciate the insights.
My pleasure. It leaves us with a final thought, though, maybe something for you listeners to mull over. We saw in that MetaICL paper just how powerful selecting the right few examples was for personalization, the oracle getting the job done with 5 examples instead of 19 random ones. Now, if making that practical hinges entirely on replacing that impossible oracle with some automated proxy, maybe based on acoustic similarity, what should we be focusing on right now to build that proxy? What are the key metrics for acoustic similarity that actually work well for diverse, challenging speech like dysarthria? Or what architectures are best suited for learning that similarity function quickly and accurately? Because cracking that problem seems like the immediate, crucial step needed to unlock the real-world potential of these incredibly efficient personalization techniques. That's the bridge we need to build next.